Hey there, Josie and Morgan! Thanks for agreeing to do this Vlogbrothers style video series with me. As planned, we will be discussing the thermochemistry unit together, a hot topic indeed for the science world. See what I did there? In this section, I am going to make sure I cover the vocab terms universe, system, surroundings, work, heat, and state functions. Some of these terms you already know. The universe, of course, is everything. The system is the part of the universe that we are studying, and its surroundings are, well, everything around it. For example, if you do an experiment in a beaker, that is the system. The lab is the surrounding, which, plot twist, is located in the universe. The system that we will be studying consists of a hill with a red ball named red on the top and a blue ball named blue on the bottom. Yeah, their parents weren't very good at original nomenclature. Red rolls down the hill and hits blue, which causes blue to roll away, while red sits there at the collision point. According to the law of the conservation of energy, the amount of potential energy that red had on the hilltop will be the same as the amount of thermal energy that blue ends with when friction against the grass finally slows him to a halt. No matter what happens, the energy in this system is never destroyed nor created. It is simply repurposed. This concept also applies to the first law of thermodynamics. The amount of heat lost in the system is the same as the amount of heat gained by the next system. For example, the amount of heat that an ice cube gains while it melts is the same value as the amount of heat the surrounding water loses as it melts that ice cube. There are two ways to transfer energy, through work or through heat. Work is defined as a force acting over a distance. Heat is defined as the transfer of energy between objects due to temperature difference. Remember, it is not the temperature that we are focusing on, but the energy transfer that is causing the temperature to change. In our thought experiment, red has done work on blue by hitting him with enough force to transfer her kinetic energy over to him. If the friction of the grass makes red roll too slowly to move blue upon collision, then the system contains plenty of heat from friction, but no work. This brings us to a new vocab word, pathway. The pathway is the route that the system has to take in order for its energy transfer to happen. The pathway in our system was that of red rolling down the hill, hitting blue, and then blue rolling away. Then there are state functions. A state function is any variable in a system that does not change depending on the pathway. This concept can be kind of tricky, so let me rephrase. The value of a state function does not change based on the steps that the system took in order to arrive at its current state. For example, in our thought experiment, energy would be a state function because no matter what the pathway was, the amount of energy in the whole system did not change. Heat and work would not be a state function because you can end up with different amounts of heat and work depending on things like friction that would affect how red rolls down to collide with blue. Now that we have the basics down, we can start dipping our toes into the pool of mathematics that goes along with these concepts. The equation I will be showing you is Q equals mc delta T, where Q is heat, m is the total mass in grams, C is the heat capacity, which is joules over degrees Celsius, and delta T is the change in temperature, which will be degrees Celsius. For problems like these, you may need to convert to joules first, so here's a handy list of conversions for you. I would elaborate further on this equation, but I don't want to cut in on the example problems Ms. Layman's will be giving in class. I hope my explanation at least provides a good foundation for our exploration of thermochemistry. The stage is yours, Josie. Over and out.
Thanks, Tiani, and as always, I'll talk to you later. And hey, Morgan, are you ready for today? Because we're going to be talking about Hess's problems and a few other things, so let's get started. Alright, so sign conventions in thermodynamics. So let's say we have a system right here. So when heat is flowing into the system, it becomes more positive because we are adding heat into the system. This creates an endothermic process. So that means when delta E is greater than 0, it is positive. And then on the other spectrum, when the system is losing heat or giving off heat, it becomes negative. And that's an exothermic process because the system's energy is decreasing. So when delta E is less than 0, it is negative and it's exothermic. So there you have it, sign conventions in thermodynamics. Alright, so I'm just going to do a quick introduction on enthalpy with you. And I'm not going to do any examples or problems with you. I'm just going to quickly explain what's going on. And Morgan will be able to do the problems or examples with you later on in the video. So let's get started. So if a chemical reaction occurs at constant pressure, as all of our chemical reactions do, we can consider a property called enthalpy. So enthalpy, which is represented by the H, is the energy or heat content of a system at constant pressure. So we can't actually measure energy or enthalpy of a substance, but we can measure the change in enthalpy for a reaction. And this change is symbolized by this right here. So it reads delta H, and in the subscripts, I've seen it written RXN or reaction. Either way works, but those two are usually the common ones. It just depends on where you're looking for your information. So now I'm going to explain what happens to enthalpy in an exothermic reaction and an endothermic reaction. So for exothermic reactions, enthalpy values are always negative. That is, the energy of the product is lower than that of the reactants. This is because energy is released as new bonds are formed in the products, and this amount of energy is greater than the energy required to break the old bonds in the reactants. So we have this equation on the board, and it just says the change in enthalpy equals H products minus H reactants. So we are changing the energy by using the products and minusing the reactants. So since the products have a small number and the reactants have a big number, it will equal a negative number, because when you have smaller and then you minus a bigger one, it always ends up negative. Since it's negative, since the enthalpy value is negative, it's an exothermic reaction. So now on the other spectrum, for endothermic reactions, enthalpy values are always positive. That is, that energies of the products is greater than that of the reactants. This is because the energy released as new bonds are formed in the products is less than the energy required to break the bonds in the reactants. So when the products, which is HP, is bigger than the reactants, we have a positive number, because big number minus small number equals positive number. And since when the enthalpy values are positive, it's an endothermic reaction. So that is a quick overview of enthalpy and a quick introduction. And there you have it.